All right, picking up where we left off, changing gears a little bit. A function f is 1 to 1 when for a and b in its domain, f of a equals f of b implies that a equals b. That's a lot of letters. It's just saying that you have two input values, a and b, two x's, whatever, and that if those two x's give two answers, then those two answers has to mean that the two x's are the same. It's still kind of abstract, but we'll look at some examples and we'll be okay. The directions say determine algebraically whether the function is 1 to 1. Well, that's what we're about to show. It says verify graphically. Well, that's easy enough. You just pick up your graphing calculator and you look at the graph. If it passes the horizontal line test, you know it's going to be 1 to 1. So that would be the easy part of this. And then it goes on to say if the function is 1 to 1, we have to find its inverse like we did at the top of the notes. Alright, so a few examples. Here we go. Let's see, without picking up a graphing calculator, if this function right here is 1 to 1.
Sorry, I think I forgot my phone in here.
If you just think about this graph, it's the square root graph. I just shifted up 1, and it certainly passes the horizontal line test, which means it is a 1 to 1 function. So no need to verify it graphically because we just did it because we know what that function looks like mentally, and we can see in our brain that it is a 1 to 1 function. It passes the horizontal line test. But what's all this about algebraically show that it's going to be 1 to 1? All right, well, here we go. Trying to make use of this information up here, and what it means is this. For every x, you're going to replace every x with a. So let's just work with the equation here. So square root of a plus 1. Okay, so f of a has to equal f of b, meaning if we have f of b, everywhere you see x, replace it with b. So that part isn't bad. Set up two equations, one with a, one with b, replacing the x with those a's and b's, and we're saying that f of a is equal to f of b. Well, then it comes up here and says that implies that a equals b. So the next thing mathematically for us to do is subtract a 1 from both sides, so that results in square root of a equals square root of b. Alright, so we're trying to get a equals b here. So you'd square both sides, and if you square both sides, you're going to get a equals b. It's kind of a weird process, but it's not altogether difficult. Replace every x with a, every x with b, set the two equations equal, mathematically solve it, and see if you result in getting a equals b. And we did. Alright, we don't need to verify graphically. We've already done that. It says if the function is 1 to 1, which it is, find its inverse. Okay, so that's the next step. I think I'll change colors here. Alright, returning to what we did formally previously when it mentioned to do it informally, we're going to do the same thing. So the second part of this is, let me pull this equation back down here. Switch the x and y, solve for the new y. So this is y, it becomes x. This is x, this becomes y. Let's solve and get y by itself. So we're going to subtract a 1. And then I'm going to square both sides. Well, that results in my getting y equals, and I'm not going to FOIL that out. I'm just going to leave it like this. I'm going to trade sides. I'm going to rename y because I don't want to confuse it with the original y, and I'm going to rename y, I guess, with the f inverse notation. I could have called it g or anything I wanted, but I'll just do this right here. Okay, this one is kind of weird. It almost looks like we're done, but remember, this is the square root graph shifted up 1, whereas this is an entire parabola, so we have to be kind of in tune with what's going on here. So we want to restrict this for certain x values. So x greater than or equal to, we don't want x greater than or equal to 0. Okay. We actually want x greater than or equal to 1. The x value that we begin this at would be the x value that zeroes this out. I know it's kind of weird, but we want all positive values, and the way to get positive values before we even square it is to restrict x to values greater than or equal to 1. If x was 0, then you get -1 and have to square it, and that wouldn't work for the graph. So don't get hung up in this too much. It's just the 0 of this factor right here. All right, let's look at another example, B. That's a 4 actually. Okay, so let's determine algebraically whether the function is 1-to-1. If you wanted to stop the video and type this equation into your calculator and look at it, you'd probably see that this 4th degree function looks like a parabola, kind of that basic shape. It doesn't appear that it would pass the horizontal line test, so I think that we're going to algebraically be able to show, I know that we're going to be able to algebraically show that this is not 1-to-1 and confirm with the graphical piece of it. Alright, everywhere you see x, replace it with a. So a to the 4th plus 2a squared minus 6. Okay, that y value when x is a has to be equal to this y value when x is b. Yeah, so mathematically you'd add a 6 to both sides, so we're going to kind of ditch those constants and we're left with a to the 4th plus 2a squared equals b to the 4th plus 2b squared. Okay, and honestly we're kind of stuck here mathematically. It's not as obvious as, you know, what we did here. It's not as obvious as far as the next step, so we just kind of look here and we look at what we see and we go, you know what? These are both even exponents. So for these to be equal, it could be, if I did solve this, I'm going to just do dot, 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 that if a equals b, then these two would equal if they were the same input value. However, because these are even exponents, I want you to think about it for a second. In this case, what if b was negative? Well, it wouldn't matter, because when you take it to any even power, it's going to result in being back positive. So it really could be that a is equal to the opposite of b. And even the other side of that is, what if a is the negative number and b is positive? Or even better yet, what if a and b are both negative? Well, to verify that functions are 1-to-1, all we need is a equals b, not any of these others. So we can't have any of these. So what that tells us is, if we have more than one set, you know, a combination, whatever, rather than just a equals b, that it's not 1-to-1. And even more beautiful is that because it is not 1-to-1, we don't have to find its inverse. So we're going to go to the next example. All right, so just kind of think about this equation right here. It's kind of weird, but another way you can kind of write this, which maybe it makes more sense, I don't know, to use, you can slide the numerator off and take out the 1/5 and let it become what we call a constant multiplier in here. You could either unstack the fraction this way or leave it stacked, but no matter the case, I hope you see this as a linear function. And just imagine in your brain a linear function passes every single horizontal line test, or it passes the horizontal line test. Every horizontal line intersects that line in at most one point. So this has to be a 1-to-1 function, but we're going to be able to verify it, or sorry, determine it algebraically. We don't have to verify it graphically because we know it's a line, and it's automatically 1 to 1. But we are going to have to find its inverse. All right, first things first, replace x with a, replace x with b, set them equal. Oh, that's not good. That's a 4. Got ahead of myself. 3b plus 4. Now, if you don't like this format, just go back up here and replace that x with a and that x with b, set them equal to each other. All right, I'm going to multiply both sides by 5, both sides of the equation by 5, so that results in getting rid of the constant multiplier. So that's 3a plus 4 equals 3b plus 4. All right, subtract 4 from both sides. 3a equals 3b. Notice the exponents are just both the understood 1. Divide both sides by 3. And there is nothing else that's going to result from solving this equation. A equals b. We just showed algebraically that the function is 1 to 1. So now let's find its inverse. All right, so I'm going to pull back down the original function. And I'm just going to leave it in this format. It doesn't matter. I could have used either one of these. Switch the x and y. Solve for the new y. Multiply both sides of the equation by 5 first. Get rid of this division by 5. So we're going to have 5x equals 3y plus 4. Subtract a 4. Divide both sides by 3. I'm going to trade sides, put the y on the left. I could leave it stacked, but I also see that this is another line, which is good, because the inverse of a linear function is another linear function. And then the last thing I'm going to do is replace the y with the inverse notation. And again, remember that you could slide the numerator off and you're just saying it's 1/3 times quantity 5x minus 4. Either way, doesn't matter. They're both correct. Okay. All right, so that sums up our work with inverse functions.